Okay, guys. What we've got here that you're looking at, let me pull up this one, is Vivado. This will be the program that you become familiar with to program VHDL. So VHDL is a hardware description language. The two big ones are Verilog and VHDL. We use VHDL because that's used by government contractors in the government, which are large employers around here. Now that obviously matters to us because we want you to get jobs and give you the skills that are relevant in this area at the current time. Vivado is made by a company named Xilinx. They make FPGA boards that you can go out and buy and then program to interface with the real world. Now, something that's really, really important to understand is that here we are programming hardware. We are not programming software. And that has some implications for this programming language, and we'll go over that. If you don't know any languages, you might actually be at a little bit of an advantage as long as you can think logically and systematically. Because those of you that have a CS background may get confused because of things that you can do in software that are not possible in hardware. So there's a couple of things to look at this. You have over on the left-hand side that you have the flow navigator is what they call it. And the project manager is for creating new projects and setting up the settings in there. We can ignore the IP integrator for the moment. Simulation is how you test those things that you're trying to run. We can ignore this for the moment. Synthesis tries to take your code and figure out how the logic works and build things behind the screen for you so that it can be turned into hardware. And implementation is really all about actually turning it into hardware. Then once you have that, you have to program it and send it to the FPGA. Now, for most of this course, we're going to be focusing on everything pre-synthesis, which is where we make the code. And then we'll also focus on simulation because obviously we need to test that code. Okay, so there's something that's a little bit interesting with VHDL that is hard to wrap your head around. And what that's going to be is we're used to seeing gates, right? Adders, subtractors, and so on and so forth. But we're going to implement all of that in code. Now, it does have what we would call a block diagram or a block design, but I don't ever recommend this because it doesn't scale very well. It's hard to design, and I've never encountered a situation in industry where we use it. However, I'm going to show it to you because it can help you picture what's going on later. So if we were to pull up a design, so here I just hit create block design, and it's going to take just a moment. The design is empty. Okay, that's fine. So I can add some IP. IP cores are really at the heart of complicated design. And you'll notice when I pull this up, you'll have gigabit Ethernet interfaces, you'll have 2D graphics interfaces, LTE, you might have FIFOs, memory controllers, all sorts of things. Well, let's start with nice and simple. We want an adder. So I just type add in the search bar, pull up adder subtractor, boom, there we go. Now you'll notice by default, A is a 15-bit and B is a 15-bit input with S is a 14-bit output. Okay, that's fine, but we've talked about full adders before, and usually they have carry-ins and carry-outs. So what we can do is double-click on it, and it pulls up this window. This is just some of the settings, and I could come in here and say, okay, we're in add mode. Ignore this top section, the fabric input type is signed, right? Output width 15. What if we call this 1? Oh, what's it not liking? Oh, it wants it to be 15 or 16, so we can have 16-bit. That's unfortunate that it doesn't want us to do simpler than that. That's okay. There's reason for that, looking how this is implemented, but that's okay if that's limiting. Okay, so now we could have a control. So this system likes to use what we call a clock enable. This is generally good practice, but I'm going to turn it off for explanation purposes. I'm going to leave off the carry-in for now. see if this lets me. I'm unsure why it doesn't want me to have a carry out, because that'd be really nice, actually. Input width, output width. Oh, here we go. Oh, it wants 2 inputs. Okay, input width is now 2. We can add output width is 2. Man, it really does not like this. There we go. Okay, so my input widths are 2. My output, both of them are now 2, which is good. Add mode subtract, output width is 2, latency is 3. If we make the output width 3, then we can actually have the full bit without having a carry, so we're going to do that. Then control, turn off clock enable, turn on, well, carry in for now will be turned off. You'll notice that there's a synchronous clear, set, reset that you can all click. We don't need any of that at the moment, and any of that. So let's just click OK here, and now we have a little adder, right? 2 bits plus 2 bits, 3-bit output. If we want another one of those, I can just hit the plus button, go find an adder, and throw it in there and set it up. Or Control C, Control V, as I just did, works just fine. So on this one, I may want to go and change the control to have a carry in. Now, the usefulness of that will become apparent. So this system that I'm showing you right here is clocked. The adders we design don't have a clock. They're combinational, which is fine. But let's say I want to have a universal clock. I can just draw a line between these two, and this is what we would call using a net or the wire to connect the two ports called clock. So we have ports and nets. Port clock. This net is, well, we could probably name it ourselves if we really wanted to. System net property. Over here in the system net properties, there's a name. So I could call this a clock net, so that if there's ever an error with that, I at least know what it comes from, okay? Similarly, I could have it would have to come in from some sort of input, and S. Now, we know that S wants to connect to CN, but that's really not all of it, is it? Because this is a bit of an issue, because we're now connecting 3 bits back to CN. And you'll notice that I'm a little hesitant with this because I never use this setup. I never use these block diagrams. But I'm trying to do this fudging through a little bit to help you visualize what we're going to be doing in code, because that's more important. So pretend like this net is just one of the bits, bit 3, right? And then I could have, all told, a 3-bit output add up, get some 6 bits, right? Have the carry in. We could throw some inputs to these clocks, and we would be good. But we don't want to design using this block diagram. That's just not really useful for us, because as soon as it gets big, you can see how this, if I had any amount of modules in here, it would get complicated and have to follow through the connections and have all the clock running everywhere. and it can get pretty confusing. So hold this idea of an image in your head while I move on to the next step of things. Let's go back here. So this is a project that we design in 3610, your next class. This is a little bit of a peek ahead. So the code here is going to consist of a couple different pieces that you can put together. And we'll try and keep it simple so that you only have to design little pieces of it, but it's helpful to see the full picture. So the first thing that you'll see is these libraries. These libraries allow us to do different functions that we might not have if it weren't for these libraries. I really like to use this logic unsigned. There's another option. Let's see if I used it in this, this numeric standard all. Those two, one or the other of those two, I recommend using all the time. So libraries are helpful. The next thing you do is you create an entity. This is saying something like, well, this exists. And most importantly, so your entity, the entity's name is, and then you list the ports. And this is what's coming in and out of this sheet, right? So this sheet is equivalent to one of these blocks, if you think of it that way. But the sheet can also have blocks inside of blocks. And that way you can design one module at a time. So here we go. Inputs and outputs. You'll notice that there's a clock, input, a reset, and don't worry too much about the rest of these, but you can go down, look, and say the clock is an input of type standard logic. Now we'll go over some of these probably more in class because they're worth talking about, but this most common types you'll see me use are standard logic and standard logic vectors. So standard logic is just a 1 or a 0. A standard logic vector is a vector of 1s and 0s. There's nothing really fancy about that. I have to tell if it's an output or an input. Notice these are outputs. This is an input. Yeah, and then we just say end the name. So that tells us what comes in and out of it. The architecture is the next thing that we can declare. Now, this word, this is a name, we call it behavioral. This is fairly arbitrary. Don't worry too much about that particular name. But so you say architecture, name it, of the thing you're working on. So we're saying this architecture, right, this came from our entity, is, and then you have a begin that ties into that. This begin belongs to that architecture up above. And there's a whole bunch of stuff that I've done up above. But let's get into what that means. So architecture is, and here I'm creating what we call signals. Another way to name those signals is a net. So similar to this diagram, that net, you can consider these. But there's one nuance to this that I don't want you to miss, where this signal is strictly internal to this entity. So technically, this wouldn't fit unless you considered the as a signal, unless you considered this whole white space as its external entity that had no ports. Okay. So let's go back and look at this. So we have architecture of our entity has internal signals of logic vectors or logic or whatever else we need. And don't worry, I'll go into this as we build up something much simpler. I just want you to see how this can end up looking. Now, inside of this entity that I've called the 7-segment display, I want to use another component that itself has ports. Now, you'll notice I don't do anything else with these ports here. I don't have to plug them into anything. I just let the top level, you'll notice I call it top. This is what we call the top level entity that ties all of our submodules together. So here we go. This is a component that's called a UART receiver. And it has these ports that I'm going to have to do something with. Then we begin our architecture. So this is just all declaration. We're just creating signals, creating components. We could create constants even if we wanted. Then we come inside of the architecture begin. Now this is a process. Don't worry too much about that yet because that's what we could call sequential logic, and we'll deal with that later. Right now we're worried about combinational. Now combinational isn't really that difficult. So this is a whole bunch of stuff going on, but we're still inside of architecture, and I'm going to come down to a case. So a case statement is like an if statement. And if you're not familiar with if statements because you never had programming, let's jump and take care of one of those first because they're easy. So here we go. Here's some simple logic. If reset, which if you recall is a port, is 1, then I want to set this counter down to 0. That's all this is saying. This notation is a little bit more complicated than you'll have right now. So we'll walk through exactly what we're doing, but this is all it is. If, this is the notation, if condition, then statement. Else if, and this is one weird thing about VHDL, the else if drops one of the E's. If I add that E, you'll notice it changes color, gets a red squiggly line under it, letting me know that there's an error. I can mouse over it, and it says syntax error near then. Now, this gets confusing a little bit because the error is not saying else if is wrong, it's saying near then. So the then, you might come up here and go, well, what's wrong with my then? Well, that's just the closest thing that it knows there's an issue to because it sees if and if, but it doesn't have an else if or else. So, oops, sorry, bounced around a little bit there. You have to do a little bit of hunting sometimes for the debug, change it to else, everything's happening. Then, this is another interesting one. Here's the line where I'm going to do something with that component I created. Remember I had that UART receiver? Well, I create an instance of it, and I can create multiple instances of it. We're not going to yet. So there's this instance name of my receiver, has ports mapped to clock 100 megahertz, which if you recall is a port, reset is a port, data in is a port, data out, however, is a signal created right here that's a vector. So that signal doesn't have to be connected out to a port. It can be connected to, say, somewhere else. And you'll notice when I double click on things, it highlights other instances of it. Well, this is connected to this data out here, which is connected to displayed number. So this, the port inside of my UART receiver is, well, let's go look inside the UART receiver. That's the code here. I have a clock, I have reset, I have S data, P data, ready, state monitor. But we're looking at P data is my output vector. So on the top level, I have data out, which is a net plugged into the port P data. So I have net data out plugged into port P data, and then net data out is attached to a displayed number. And this differential between nets and ports is important. So let's go back here. Remember, port clock uses net to connect to other port clock. Okay, similarly, I have something called data ready. That data ready goes into a process. It's used internally. This is just another net, also called signal, declared as signals even. And then you end the architecture. Remember we called architecture behavioral earlier. This is just saying end that. Comment, you use double dash to comment things out. If you're not familiar with programming, double dash taking something out means, commenting it out means that it doesn't execute in the program. So it's just going to skip it over it. This is essentially just for human reading. Okay. So let's start from scratch with a simpler example now that we have some idea of how we cobble these things together and actually go into cobbling it together. Okay, so project. I need a new project. So let's go File, Project, New. Oh, that was open. Okay, File, Project, New. I'm just going to go Next. Let's call this ECE 2700 intro. We're going to go ahead and use an RTL project. There are no sources in here, and that's totally fine to start with. I have no constraints. Constraints are something we'll get into later. This is default part. So what this is doing is asking what is the physical thing that you're writing code for. Now in our case, we're going to be using, so I'm going to click on boards here and basis 3. Now I'll post a walkthrough that shows you how to install Vivado and get this basis 3 set up. But you just basically click the install boards and search for it. This allows us to know what hardware we have available to work with, and more importantly, tells the Vivado, the program, how to turn our code into something useful. So hit next, hit finish, and yes, I have to close my old lab. Okay, here's my new project. Nice blank project, has nothing in it. So what we're going to do is we're going to go up to this little plus sign here and do some add sources. And I want to create design sources to start. Create file is what I push here. And we're going to call this a mux because I want to make a mux. You guys are going to make an adder, and I'll leave that up to you. Okay? That's for the lab, by the way, that the adder is going to happen. I'm going to skip this window for now. You can use this to create the ports here, but I'm just going to write it out explicitly later. So I just said OK there, and now I have a mux. A few things that I can do. I can make this bigger by clicking maximize so that we can more easily see what's going on. You'll notice it creates all this commentary so that I can say that I work for Weber State and the engineer is me and so on and so forth. But I'm just going to delete that all for now because it's extraneous to the exercise. Now you'll see what's nice is it creates library IEEE use standard logic 1164. This is a very helpful library. We may talk about that in more detail later. I'm also going to uncomment all of this. Well, this is documentation. I'm going to delete this, and now I'm using the numeric standard. I really like this. Some professors will make you learn VHDL without it. I think that's a little bit insane because you will almost always use this library or a similar one that will fulfill functions. The rest of this I don't need. And really I don't need this because I'm going to try and keep this nice and simple for readability. So you'll notice that it suggests that I should have ports, and that's a good idea. I need ports. Okay, what ports does a mux have? Well, let's have it defined as a 2-input mux, right? And a mux is a word for multiplexer, if you're unfamiliar. I think I've brought it up in class once or twice. The whole thing is that it has some number of channels, and so say 2 inputs, 1 output, and then 1 input that's to tell the output which to connect up to. I'm trying to make sure that makes sense. So I have ports A and B. And let's start with it this way. I like having nice readable code. Okay, so what we're going to want to do, sorry, computer's trying to shut down on me, 2 seconds. Okay, sorry. Port A is an input of type standard logic. We end with a semicolon. Okay? I then want B. This is also an input, and it is also standard logic. I need an out. Oh, you'll notice that I just hit enter there to try and hit return, but instead it auto-filled in a suggested. So if I say standard logic, it suggests doing the 1164. I have to hit escape, and then I can finish the enter. Okay, C is our output. It is also just standard logic. And then we need one more input, and we're going to call it select. This is an input, as I said, and it is also standard logic. Oh, and this is where, so on the last one, we just delete that term. Oh, looks like select is a reserved word, so we're just going to call it cell. Okay, so I have a mux with an entity called ports, with ports A, B, C, and select. Now, I don't have any internal signals in a mux, not really, because it's such a simple module. And all it's doing is saying, based on select, choose to have C assigned to A or B. Now, there is a more elegant way to do this, but I want to just have an explicit call out for those that are unfamiliar with programming. I don't want to introduce too many ideas at once. So we start with an if statement. If, well, we want to choose on select. Select is equal to 1. Okay, then I need to do something. What do I do? Oh, wait, let's start with if select is 0. Then C is equal to A. Else, and I could do else if, right? Else if select, but select is only 0 or 1. I don't need everything. So if it's 0, choose A. Otherwise, C is B. That's all a mux does. Then I end if. Let's see, what did I do wrong here? Oh, no, that's fine. You'll notice that I accidentally capitalized this. That's not an issue. VHDL is pretty much case insensitive. So something to be aware of. Oh my gosh, does this need to be in a process? I always forget. VHDL does not like if statements outside of processes. And so something I'll be honest with you guys, I don't come from a VHDL background. I come from a Verilog background. As far as the thinking goes, it's correct, but you may see me every once in a while get hung up for a moment on little things like that where the if statement needs to be in a process. So what all this process is saying is this is what we call a sensitivity list, and it's going to react to whatever's inside the process is going to react to everything or anything inside of this list changing. So if A changes, B changes, or select changes, this is all going to update. So it goes process, one of these changes, and then decides if select is 0, otherwise this. So it's useful to have A, B, and select, because if I said just A and B, we might run into an issue because B updates and C is assigned to B, but this won't execute because B changed and is not on the sensitivity list. Therefore, this if statement won't be evaluated, and I'll just hang on to the old value of B. That's the quick version of a sensitivity list. We'll get way more into detail on processes and sensitivity lists and similar things. Okay, so now I have a little module called mux. Great. So let's go ahead and back out sources, and create, with a little plus sign, a new. So I need to create or design sources, okay? This one, create file, it's gonna be VHDL. I'm gonna call it top. Okay, hit finish, hit okay. Okay, so top, we start out exactly the same. There's nothing fundamentally different about this. But we're going to treat this as something a little bit special because it's our top level module. I'm not going to worry about any ports on this just yet because maybe we don't know what it is. But this time, let's say that I want to use these this 2 input mux to create a 4 input mux. We're going to do that by cascading the muxes. In order to do that, we need internal signals now, right? So signal, we should probably not tab this one just for consistency. Signal, we'll call this C1. And it's going to be, sorry, I need a drink real quick. Okay, so signal C1 needs to be standard logic. Got really distracted there for a minute, guys, sorry. Because that's the output of our component, right, our box. So there, signal C1 is standard logic. Similar, I need a signal C2, and that's standard logic. Ooh, forgot the underscore. So there now are 4 inputs, but these, because well, not quite yet. Let's declare our component, just so we can remember what we're doing. So the component is a mux, okay? And that component has ports in it. And those ports are going to be A, of type standard logic. I always forget this one right quick. Shoot, maybe that in. It's going to have B of standard logic. It probably made sense if I had copied and pasted this standard logic rather than type it in a million times, but I think it will survive. Okay, so A, B, and C of standard logic, and then I also have select of standard logic. Okay, great. Sorry, worried that I screwed something. Oh, that's what I screwed up. And then I have to end component. So that begin was giving me an error before I had this. And you'll notice if I mouse over, it says error near begin. That usually means that the previous line is the problem. And it's really hard to debug if I've missed an end component and have a lot of code. Fortunately, that one was really easy. Something to be aware of. Okay, so now we can start stringing these up a little bit. So I need to declare these muxes. So I have mux1, okay? And all this is going to do, so I have a component, and now I need instances of these components. The instances allow me to reuse my code. I don't have to write a new mux every time that I want to implement one. I just create a new instance of it. And earlier you saw me use these ports in a port map, but we're going to do it a little bit differently this time. And this is what we call explicit port mapping. And I recommend strongly to do it this way, where you're going to tell it that your port Here's an issue that I almost forgot. So we're going to have inputs of A, B, C, and D, and I need to tell them explicitly where to go. So let's call them top A top, B top, C top. How about that? That may be weird. Underscores. Sorry, I didn't think about this signal naming. AA, BB, CC. Yeah, I like that. We'll just go with that. So AA gets mapped to, and sometimes I screw this one up, A. Similarly, BB gets mapped to B. We're going to have, we need two selects if we're going to have two muxes, right? That makes sense. So we're going to have select one get mapped, or well, let's be zero index. That's smarter. Gets mapped to cell. So you'll notice I'm just mapping A, B, cell, and now I need C, which is, we already called C1. Let's back this up and call it C0 and C1, so we're back to zero index because VHDL is zero index and it's helpful to think that way. C. Oh, and this is one of the issues I always do with VHDL is this is separated by commas. Did I put this backwards? Sometimes I do that. Nope. Oh, AA is not declared. That I can deal with. So the issue is that I don't have those inputs. I need AA, BB, CC, or sorry, I have C0s. And these are in of standard logics. I also need select to be, well, I need two selects at least, right? So let's make it an input of type, I really wish this one over. So it's a select input standard logic vector. And this notation may be a little bit weird for you guys. We're going to do 1 down to 0. Log vector, that's it. Logic vector. Okay, so now I have two inputs, AA, BB of int types. But I know I'm going to need more than that, right? Because I need CC and DD. So you'll notice that if they're the same type, I can put them on the same line and then just say they're all inputs of standard logic type. That's nice. Now, I've changed this around a little bit. So I've tried mapping select to cell 0, but that's not really what I did because I now said, well, select is now a port and it's a standard logic vector. So let's change it and say it's select at location 0, right? So now I'm just accessing one element of that vector. And since a single element of a logic vector is a bit, I can use that standard logic to plug it in there. Yeah, so there we go. I've mapped max1. So if I want to create a second mux, we can start simply by copy and pasting and renaming it to mux2. This one is no longer mapped from AAA. So net AA, this is actually going to get a little bit confusing. I don't want it to. So the outside world is going to see this port of AA, internally AA is allowed to be a net. And that can get confusing, but hopefully it's clear. So externally, it sees a port AA. Internally, I now have a signal of AA. Now, I also have CC and DD, so let's change that. And I want to change the select. I'm no longer accessing the 0th element. I now want to access the first element. Okay, and then C is now mapped to C1. So now I have 2 muxes. That's really good. And I just hit save. You'll notice something else changed. I now, up here on the top left, I have a top level module. That's what this is, with 2 instances of mux. Inside of it, mux1 and mux2. So this allows me to start seeing the hierarchy, vocabulary word therefore. So there's a hierarchical design. So it's going to see the hierarchy of how my components are put together. Okay, so I have 2 muxes. The outputs, they're C0 and C1. But there's an issue, is I wanted to be able to select just one of these. This is not the best way to do this, because in order to do it this way, the way I'm implementing this, I'm going to have a 4-to-1 mux, but I'm going to need actually 3 select signals, which isn't going to be very good. It's not optimal, but it'll work. Okay, so let's create a mux 3. Now visualize with me, right? So these are the nets that are plugged into these specific ports. So if you recall way back, I don't have it pulled up anymore with how I was showing those block diagrams. The port is A, the net or signal is CCDD, and an output net of C1. Okay, so these are, CCDD, are now wires that are connecting from each of these little blocks together. And this is how it should kind of exist inside of your head. So what I'm going to do then is say, instead of having AA and BB, I'm actually going to use these signals that I created of C0 and C1. Okay. So now this 2-to-1 mux and this 2-to-1 mux, the outputs are now plugging into the input of this 2-to-1 mux. And now I'm going to have the output. And we're going to call it the C out. It is a type output. Sorry, it is an output of type standard logic. I had some minor syntax errors when I made that change. Okay, now I have C out that is internally a net and externally a port. And I'm just going to go down here and say this is C out. Okay, so this is a new error that I haven't encountered before. It's just saying that it doesn't like having this port plugged directly into that port. So it needs some sort of buffer in between these 2 of them. Let's see if we can't do that the most simple way, where I'm going to have this be C intermediate. I'm going to create a signal of C intermediate that's a standard logic. And then I will just assign sorry, what was I doing? I need C out gets assigned to C int. There we go. And that is always true. So this, notice there's no process involved in all of this. This is all then just combinational. You don't have to worry about what's going on behind the scenes in the muxes. You just know that each of these outputs are working together. You'll also notice that I use this equal sign rather than just equal. This is the hardware assign. We'll get into some nuts and bolts of that, but I think that's probably a long enough kind of introduction to what VHDL is. and how to program with it. I'm really hoping that this doesn't end up being more confusing than it is helpful, because this is fairly simple programming, and we'll get into making an adder as part of the lab, and I think that's really where you will really learn a lot more, is actually doing it yourself. But what I wanted to show you is the general components. So let's do a quick review of that. First component, library. This is allow you to use things. The entity is creating the box, as in the when I was stringing the box together, that's saying that this box is here, it has these ports. The architecture is how things are wired together, or what their behavior is, right? That's why we call it behavioral. Signals then can get declared. These are used only internally. They're not accessible outside of the box that we've created in the entity, but we need them to connect any smaller components together. Okay, so we have a component then, which is something else we went through and created. I've created multiple instances of that one component and then wired them together using inputs from the ports and signals or nets to wire them together. You saw me mousing over some things to see errors, and then ta-da, we have this component. The next step of this is creating what we would call a test bench to make sure that works. I'll save that for another video, but hopefully this video serves as something of a useful tool. All right, and good luck.